Look up at the night sky. What do you see? A vast, swirling expanse of stars, galaxies, and nebulae, all seemingly thrown together in a cosmic free-for-all. It's easy to think of the universe as a place of pure chaos, where colossal explosions and violent collisions happen without rhyme or reason. But what if I told you that beneath this turbulent surface, there's an intricate order, a hidden symphony playing out across the cosmos? Patterns so precise, so elegant, they've been guiding the universe since the very beginning. This is the secret truth of our reality. Chaos isn't random at all. It's just order waiting to be understood. Think about the way galaxies spiral, their arms curling like delicate seashells, or how lightning forks in jagged yet mathematically perfect branches. Even the seemingly random dance of subatomic particles follows rules we're only now beginning to decode. From the smallest quantum fluctuations to the grandest cosmic structures, there's a rhythm, a logic, a hidden language written into the fabric of space and time. And today, we're going to unravel that language together. We'll explore how the universe takes chaos and weaves it into harmony, how destruction gives birth to creation, and how what looks like randomness is actually part of a grander design. By the time we're done, you'll never look at the night sky the same way again. Because once you see the patterns, once you recognize the delicate balance between turbulence and order, you'll realize the cosmos isn't just a wild, untamed place. It's a masterpiece, a puzzle where every piece fits perfectly, even when it doesn't seem to. So let's begin this journey, peeling back the layers of cosmic chaos to reveal the astonishing order beneath. The universe has kept these secrets long enough. It's time to uncover them. Take something as seemingly unpredictable as a supernova, a star exploding with the energy of a billion suns. At first, it looks like pure cosmic mayhem, a violent outburst defying any pattern. Yet astronomers have found that these explosions follow precise physical laws. The brightness, the way the shockwaves ripple outward, even the elements forged in the blast, all of it can be calculated, predicted, understood. That's the paradox of our universe. What dazzles us as chaos is just mathematics in motion. Look closer and you'll find these hidden rules everywhere. Spiral galaxies, for instance, don't just twist randomly. Their arms unfurl in near-perfect logarithmic spirals, mirroring the same Fibonacci sequence seen in sunflower seeds or nautilus shells. Even the distribution of galaxies across the cosmos isn't haphazard. They cluster in vast, web-like structures, following gravitational blueprints laid down in the universe's infancy. And then there's the quantum realm, where particles pop in and out of existence in what seems like pure randomness, except even here, there's a method. Quantum mechanics gives us probabilities, not pure chance. Flip a coin enough times, and the randomness averages out to a predictable 50-50 split. The universe works the same way, so why does chaos feel so real? Because we're seeing only a fragment of the pattern. Think of it like watching a single ripple in a pond. You can't see the entire wave, but that doesn't mean the physics isn't there. From the tiniest particles to the largest galactic superclusters, the cosmos is a tapestry of interlocking laws, each thread precisely placed. What we call randomness is just the gap between our understanding and the universe's perfect order. And every discovery, from Newton's gravity to Einstein's relativity, has been a step toward closing that gap. The more we learn, the clearer it becomes. Chaos isn't the rule. It's the exception, and even then, only to our eyes. Fractals might just be the universe's best-kept secret, a silent code, etched into everything from the veins of a leaf to the sprawling arms of distant galaxies. These infinitely repeating patterns, where tiny fragments mirror the whole, show up in the most unexpected places. Take a glance at a coastline from space, and you'll see the same jagged edges whether you're zoomed in or out. Now look at a nebula with its turbulent clouds of gas and dust, and you'll spot the same swirling shapes at every scale. It's as if the cosmos has a favorite design, one it can't stop reusing. The Mandelbrot set, one of the most famous fractals, is a perfect example. Zoom into its intricate borders and you'll find smaller versions of itself, each with the same elaborate twists and turns. Remarkably, this mathematical curiosity isn't just a pretty abstraction, it mirrors the way galaxies cluster along vast cosmic webs, their filaments branching out like an unfathomably large neural network. Even the distribution of matter in the universe follows fractal-like rules, with dense clusters giving way to finer and finer structures. It's no wonder scientists use these patterns to model everything from how stars ignite inside nebulae to the way dark matter sculpts the universe itself. What's truly mind-bending is that fractals aren't just a quirk of geometry, they're a signature of efficiency. Nature loves them because they're the simplest way to build complexity. A river doesn't need a blueprint to carve its winding path. It just follows the same erosion patterns over and over, creating tributaries within tributaries. In the same way, the universe doesn't waste energy reinventing the wheel. Whether it's the lightning bolt splitting the sky or the delicate branching of a tree's roots, the same rules apply. Chaos, then, isn't the absence of order. It's order operating on a scale so vast, so layered, that our minds struggle to see the full picture. This hidden symmetry even extends to the quantum realm. At the smallest scales, particles fluctuate in ways that seem utterly random, until you realize their probabilities form wave-like patterns that repeat and ripple outward. From the tiniest vibrations of strings in theoretical physics to the grand sweep of galaxy superclusters, fractals bridge the gap between the infinitesimal and the infinite. They're proof that the universe speaks in echoes, repeating its favorite motifs across time and space. What we perceive as disorder is often just a fragment of a larger, breathtaking pattern, one we're only beginning to decode. There's a number that seems to whisper through the fabric of the universe: 1.618, the golden ratio. Artists have used it to create masterpieces, architects to design timeless structures, and nature to shape everything from flower petals to hurricane spirals. But this mathematical marvel doesn't stop at Earth's boundaries. It's woven into the very architecture of space itself, turning what looks like celestial randomness into a symphony of precision. Take the Milky Way. From afar, it appears as a whirlpool of stars, its spiral arms stretching outward in what seems like a freeform dance. Yet those arms aren't just sprawling haphazardly. They follow a logarithmic spiral, growing wider at a rate that precisely matches the golden ratio. The same pattern repeats in galaxy after galaxy, as if the cosmos has a favorite blueprint. Even more astonishing, this ratio pops up in the orbits of planets and moons. Saturn's rings, for instance, divide into sections that echo the ratio's proportions, while some planetary orbits align with it in ways that defy mere coincidence. Why does this number hold such cosmic sway? It all comes down to efficiency. The golden ratio represents a kind of mathematical sweet spot, a balance between expansion and structure. In galaxies, it allows for maximum star formation while maintaining stability. In orbital mechanics, it creates resonant harmonies that keep celestial bodies from colliding. It's as if the universe, faced with infinite possibilities, keeps returning to this one elegant solution, a hidden rulebook for building beauty. But here's the real kicker. The golden ratio isn't just a passive observer in the cosmos. It's an active participant. When galaxies collide, their mergers often settle into new shapes that still honor the ratio. When stars explode, the debris swirls into nebulae with the same familiar spirals. Even the distribution of matter in the universe on the grandest scales seems to echo this proportion. It's a reminder that chaos isn't the absence of order, it's order in motion, rearranging itself according to timeless rules. So the next time you gaze at a spiral galaxy or trace the path of a planet's orbit, remember, you're not just seeing randomness, you're witnessing a number, an ancient, unshakable constant quietly shaping the universe, one perfect curve at a time. Imagine a butterfly flapping its wings in Brazil, tiny, insignificant, right? Yet that minuscule motion could theoretically set off a chain reaction leading to a tornado halfway across the world. This is the butterfly effect, the heart of chaos theory, and it doesn't just apply to Earth's weather. The cosmos has its own version of this phenomenon, where the tiniest shifts can rewrite the fate of entire star systems. Take something as seemingly stable as our solar system. For centuries, we thought of planetary orbits as clockwork, predictable, unchanging. But chaos theory reveals a different truth. A slight gravitational tug from a passing star, a nudge from a distant galaxy, even the accumulated push of sunlight on an asteroid, these microscopic forces can, over millennia, send planets spiraling into new orbits. Astronomers call this orbital chaos, and it's why predicting the solar system's fate billions of years from now isn't just hard, it's fundamentally impossible. The universe remembers every tiny disturbance, amplifying them into cosmic upheavals. Nowhere is this more dramatic than with near-Earth asteroids. A space rock millions of miles away might seem harmless, but chaos theory shows how a single close encounter with Jupiter could bend its trajectory straight toward us. Scientists use chaos math to calculate these keyhole, moment-specific points in space where a small change today means a catastrophic impact centuries later. It's like cosmic foresight. By mapping these chaotic pathways, we can spot dangers long before they arrive. Then there's the Sun, our seemingly steady star. Solar flares, those eruptions of plasma that can knock out satellites and power grids, might look random, but dig deeper and you'll find patterns. The Sun's magnetic field tangles and snaps like an over-twisted rubber band, and chaos theory helps predict when that energy will burst free. By tracking tiny magnetic shifts, scientists can forecast solar storms with surprising accuracy, giving astronauts and power grids precious hours to prepare. Even the weather on other planets obeys these rules. Mars' dust storms, which can engulf the entire planet, start as local breezes, small disturbances that grow exponentially. Jupiter's Great Red Spot, a storm larger than Earth, thrives on chaos, swirling for centuries because of microscopic eddies feeding its fury. These aren't anomalies, they're the universe's way of reminding us that chaos isn't lawless. It's a different kind of order, one where every flutter, every ripple, every whisper of gravity is a note in an endless cosmic symphony. So the next time you hear about a near-miss asteroid or a solar flare, remember, what looks like randomness is just the universe playing out its most intricate equations. Chaos isn't the absence of rules, it's the rules working in ways we're only beginning to grasp. And with every discovery, we're learning to read the cosmos's most turbulent handwriting. If spacetime were a calm ocean, quantum foam would be the boiling turbulence beneath its surface, a seething, unpredictable dance of particles appearing and vanishing in trillionths of a second. This isn't science fiction, it's the bizarre reality of the universe at its smallest scales. Picture a cosmic bubble bath, where space itself churns with energy, constantly birthing pairs of particles and antiparticles that annihilate each other almost instantly. These fleeting disturbances aren't just random noise, they're the hidden scaffolding of reality, shaping everything from the gravity of black holes to the accelerating expansion of the cosmos. What's truly mind-bending is how this quantum chaos connects to the universe's largest structures. Take black holes, for example. At their edges, where gravity warps spacetime to its limits, quantum foam becomes a frenzy of activity. Virtual particles popping into existence near the event horizon can get torn apart, one swallowed by the black hole, the other escaping as radiation. This process, predicted by Stephen Hawking, slowly evaporates black holes over eons. It's a perfect marriage of quantum unpredictability and cosmic scale consequences, proving that the tiniest fluctuations can alter the fate of the universe's most monstrous objects. Then there's dark energy, the mysterious force accelerating the expansion of the universe. Some theories suggest quantum foam might be its source. Every cubic centimeter of empty space isn't really empty. It's a frothing sea of energy, and that energy could be pushing space itself apart. If true, it means the same quantum chaos that governs particles smaller than atoms is also driving the evolution of galaxies billions of light years apart. But the most tantalizing possibility, quantum foam might be the key to uniting Einstein's theory of relativity with quantum mechanics, the holy grail of physics. Relativity paints spacetime as smooth and continuous, while quantum mechanics insists it's grainy and unpredictable. Quantum foam sits right at THAT, Chinese letter, offering clues to a deeper theory where both can coexist. Imagine spacetime not as a static stage but as a dynamic, ever-shifting fabric, its wrinkles and folds dictated by the same quantum rules that govern particles. This isn't just theoretical musing. Experiments like gravitational wave detectors and quantum gravity probes are hunting for ripples in spacetime that could reveal foam-like structures. Even the humble GPS in your phone relies on corrections for spacetime's quirks, proof that quantum chaos isn't just abstract physics. It's woven into the tools we use every day. So the next time you stare into the night sky, remember, the vast, serene cosmos you see is built atop a foundation of infinite turbulence. What looks like empty space is alive with creation and destruction, a ceaseless dance that powers black holes, fuels dark energy, and might one day unlock the universe's deepest secrets. The foam isn't just beneath spacetime, it is spacetime, and we're only beginning to understand its rhythms. Black holes defy everything we think we know about order and chaos. They're the universe's ultimate paradox, cosmic vacuum cleaners that devour everything in their path, yet somehow, they're also the engines that build galaxies. Picture a black hole not as a mindless destroyer, but as a sculptor, shaping the cosmos with the same precision as a potter molding clay. Their gravitational pull is so strong that not even light can escape, yet the energy they release can ignite quasars brighter than 1 trillion suns. At the heart of every black hole lies the event horizon, a point of no return where space and time warp beyond recognition. Cross this invisible boundary, and the laws of physics as we know them unravel. Yet, just outside this chaotic abyss, something remarkable happens. Matter spiraling into the black hole doesn't just vanish, it superheats, creating swirling disks of plasma that glow with X-rays and gamma rays. These accretion disks aren't just cosmic death throes, they're power plants converting gravity into radiation so intense it can outshine entire galaxies. Then there's Hawking radiation, the ghostly whisper that proved black holes aren't eternal. Stephen Hawking stunned the world when he revealed that, thanks to quantum fluctuations near the event horizon, black holes slowly leak particles, evaporating over unimaginable timescales. It's a perfect marriage of chaos and order. the unpredictable quantum foam at the tiniest scales dictating the lifespan of the universe's most massive objects. But black holes don't just destroy, they create. Supermassive black holes lurking at the centers of galaxies act like gravitational anchors, their immense pull organizing stars into orderly orbits. Without them, galaxies might spiral into disarray. Even more astonishing, the jets of particles they blast outward at near light speed can trigger star formation, seeding new solar systems in their wake. It's as if the universe designed black holes not just as traps, but as catalysts chaotic by nature, yet indispensable to cosmic structure. So the next time you hear about a black hole's terrifying appetite, remember, these aren't just monsters lurking in the dark. They're the architects of the cosmos, turning chaos into creation, destruction into rebirth. The universe doesn't just tolerate black holes, it depends on them. Dark matter is the universe's silent architect, an invisible force shaping everything from the smallest galaxies to the largest cosmic webs. Picture it like the scaffolding of a building. You don't see it, but without it, the entire structure would collapse. This mysterious substance doesn't glow, reflect, or absorb light. Yet its gravitational grip is so powerful that it dictates how stars whirl around galactic centers and how galaxy clusters move through space. Without dark matter, the Milky Way would spin itself apart, and the universe as we know it would be a scattered, formless void. But how do we study something we can't see? Astronomers have a clever trick: gravitational lensing. When light from distant galaxies travels through the cosmos, dark matter's gravity bends its path like a lens warping an image. By mapping these distortions, scientists can trace dark matter's hidden contours, revealing vast halos around galaxies and filamentary bridges connecting clusters across billions of light years. It's like watching wind move through a field of grass. You don't see the breeze itself, but the way the blades bend tells you it's there. What's truly astonishing is how dark matter brings order to chaos. Take the Bullet Cluster, where two galaxy clusters collided in one of the most violent events in the universe. The visible gas smashed together and heated up, but the dark matter, detected only by its gravitational shadow, passed right through, untouched. This proved dark matter isn't just some vague idea. It's a physical substance with structure, one that holds galaxies together even as visible matter scatters. Then there's the cosmic web, the universe's grand blueprint. Dark matter forms an intricate lattice, with galaxies clinging to its threads like dew on a spider's silk. Without this web, galaxies would never have clumped together in the early universe, and stars might never have ignited. Dark matter isn't just another component of the cosmos, it's the framework that made life possible. Yet for all its power, dark matter remains elusive. Is it a sea of undiscovered particles, a flaw in our understanding of gravity? Every experiment, from deep underground detectors to space telescopes, brings us closer to unraveling the mystery. One thing's certain: the universe isn't just held together by the matter we see. It's the invisible hand of dark matter, quietly weaving order into the chaos that keeps the cosmos from flying apart. And as we peel back its secrets, we're not just learning about hidden matter, we're rewriting the story of how the universe works. The cosmic microwave background is like the universe's baby picture, a faint glow that's traveled across space for over 13 billion years, carrying secrets from the very first moments of existence. Stretch out your hand, and a tiny fraction of the static on an old television screen comes from this ancient light, whispering clues about how everything began. But this isn't just random noise. Those subtle variations in temperature, some patches warmer, others cooler by mere millionths of a degree, are cosmic fingerprints, the imprints of density fluctuations that would one day grow into galaxies, stars, and planets. What's astonishing is how smooth the early universe was. The CMB reveals a cosmos that began with near-perfect uniformity, like a pond frozen in time before the first ripple. Those tiny temperature differences, they're the gravitational seeds, the slight overdensities where matter would eventually clump together under its own weight. Over eons, these minuscule wrinkles amplified, pulled by gravity into the vast cosmic web we see today, threads of galaxies stretching across the void. It's as if the universe left us a coded message in its very first light, a blueprint for how chaos would later emerge from order. Scientists decode this message using instruments like the Planck satellite, which mapped the CMB with unprecedented precision. The patterns it found weren't random, they matched predictions of cosmic inflation, the theory that the universe underwent an exponential expansion in its first fraction of a second. Think of blowing up a balloon with microscopic writing. As it inflates, the words stretch but remain coherent. Inflation did the same to quantum fluctuations, magnifying them into the large-scale structures we now observe. But the CMB holds even deeper mysteries. Some of its features, like the cold spot, an unusually large, cool region, hint at physics beyond our current understanding. Could it be evidence of parallel universes brushing against ours, or a flaw in inflation's elegant story? Then there's the cosmic dipole, a subtle temperature gradient suggesting our galaxy is moving through space at over 1 million miles per hour, pulled by unseen gravitational forces. The CMB isn't just a relic, it's an active puzzle, challenging us to rethink the universe's origins. Most remarkably, this ancient light connects directly to the here and now. The same physics that imprinted patterns on the CMB governs how galaxies spin, how black holes merge, even how Earth formed in a quiet corner of the Milky Way. When you look up at the stars, you're seeing the end result of processes that began as quantum ripples in the fiery dawn of time. The universe didn't descend into chaos, it unfolded according to a hidden script, written in the language of light and gravity, waiting for us to read it. Picture plucking a guitar string. Each vibration produces a different note, a unique frequency that sings through the air. Now imagine that every particle in the universe, from the electrons whirling around atoms to the photons carrying light across galaxies, isn't a point but a tiny, shimmering string. These strings don't just sit there, they vibrate, twist, and resonate in hidden dimensions, their harmonies shaping the very fabric of reality. This is the breathtaking vision of string theory, where the cosmos isn't a collection of chaotic collisions but an intricate symphony, each note a fundamental force, each chord a law of physics. At its core, string theory is an attempt to solve the universe's greatest puzzle. Why do gravity and quantum mechanics refuse to play by the same rules? Einstein's relativity paints spacetime as a smooth, bending canvas, while quantum mechanics insists it's a frothing sea of unpredictability. String theory bridges this divide by suggesting that the contradictions vanish if we zoom in far enough down to scales a billion times smaller than an atom. There, particles aren't dots but loops or snippets of energy vibrating at precise frequencies. A string wiggling one way might be an electron, another twist, and it's a quark. The math is stunning. These tiny oscillations could explain every force, every particle in a single framework. But here's where it gets even wilder. For the equations to work, strings can't just dance in the 3 dimensions we know. They need room to move, 6 or 7 extra dimensions, curled up so tightly we'd never notice them. Think of a garden hose. From a distance, it looks like a simple line, but up close, you see it's a cylinder. String theory suggests the universe might be like that, with hidden dimensions folded into every point in space. These extra dimensions aren't arbitrary, their shapes determine how strings vibrate, which in turn sets the laws of physics. Change the geometry, and you'd rewrite reality itself. What's mesmerizing is how this idea turns chaos into harmony. Take the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. In string theory, they're not separate phenomena but different notes played by strings. Even the bewildering zoo of subatomic particles fits into this musical framework. The universe isn't a jumble of unrelated pieces. It's a composition where every element emerges from the same underlying theme. Yet string theory isn't without its skeptics. For all its elegance, it's notoriously hard to test. The strings are too tiny, the energies too extreme for current experiments to detect. Some argue it's more philosophy than physics, a beautiful idea without proof. But others point to indirect clues, like the way black holes' entropy aligns perfectly with string theory's predictions, or how certain higher dimensional shapes mirror the patterns we see in particle collisions. The theory also offers a tantalizing possibility that the Big Bang wasn't the beginning but a rebound, a moment when strings stretched to their limit and snapped back, birthing our universe in the process. Whether string theory ultimately holds up or not, its real gift might be the way it reshapes how we see the cosmos. It suggests that beneath the apparent chaos of exploding stars, colliding particles, and warping spacetime, there's a deeper order, a universal score waiting to be deciphered. And if we ever learn to read it, we might just find that the universe isn't just governed by laws but composed of music, a celestial melody playing out across hidden dimensions, with every atom, every galaxy singing its part. Entropy is often called the universe's arrow, the relentless force that pushes everything toward disorder. Scramble a deck of cards, and they'll never shuffle themselves back into order. Leave a sandcastle on the beach, and the tide will inevitably scatter it. On cosmic scales, stars burn out, galaxies drift apart, and even black holes slowly evaporate, all seemingly marching toward a cold, uniform end. But here's the twist. While entropy dictates the big picture, pockets of the universe rebel, creating islands of order in the sea of chaos. Life itself is the ultimate act of defiance, a phenomenon that takes scattered molecules and assembles them into intricate, self-replicating structures. Take a single cell in your body. It's a marvel of organization, with proteins folding into precise shapes, DNA encoding vast libraries of information, and molecular machines working in perfect synchrony. All of this happens while the universe around it tends toward disarray. Even stars, those titanic furnaces, are engines of order. They fuse chaotic clouds of hydrogen into heavier elements, forging the building blocks of planets and life. A supernova might seem like pure destruction, but in its wake, it scatters iron, carbon, and oxygen across space, raw materials for new worlds. The universe isn't just falling apart, it's constantly rearranging itself, trading global chaos for local complexity. Black holes play a surprising role in this dance. They're often seen as cosmic shredders, swallowing matter and information without a trace. Yet, according to the laws of thermodynamics, they are also entropy powerhouses. As matter spirals into a black hole, the entropy of the system skyrockets, not because the hole itself is disordered, but because it hides that disorder behind its event horizon. In a way, black holes are the universe's pressure valves, absorbing chaos so that order can flourish elsewhere. Some theories even suggest that the information swallowed by black holes isn't truly lost but encoded on their surfaces, a holographic record of everything they've consumed. Then there's dark energy, the mysterious force accelerating the expansion of the universe. As space stretches, entropy grows, but so does the potential for new structures to emerge. Distant galaxies may fade from view, but in the voids between them, quantum fluctuations could birth entirely new universes, each with its own laws and possibilities. Entropy isn't just about decay, It's about transformation, a cycle where the dissolution of one system becomes the raw material for the next. So while the universe may be doomed to eventual heat death, that's only half the story. For billions of years, perhaps trillions, it will teem with complexity, from swirling galaxies to thinking minds. Entropy doesn't erase order, it redistributes it, ensuring that even as some structures crumble, others rise in their place. The cosmos isn't a one-way slide into chaos. It's a dynamic, ever-shifting balance, a dance of destruction and creation that's been playing out since the very first moment of time. A single pebble tossed into a still pond sends ripples expanding outward, each wave influencing the next, but in space, those ripples can reshape entire worlds. Consider an asteroid no bigger than a skyscraper drifting near Mars. Its gravity is minuscule, barely a whisper against a planet's pull. Yet over millions of years, that tiny tug can nudge Mars' orbit just enough to alter its climate, shifting dust storms into new patterns or exposing frozen water reserves to sunlight. It's a cosmic domino effect, where one small change today rewrites a planet's destiny tomorrow. Now zoom out to our solar system's chaotic ballet. Jupiter, the heavyweight of the planets, doesn't just orbit the sun, it waltzes with every passing comet and asteroid, its gravity slinging some toward the inner planets while ejecting others into interstellar space. A single close encounter with a rogue object might seem insignificant, but chaos theory reveals the truth. These interactions are cosmic calculators, compounding tiny nudges into planetary scale shifts. Astronomers call it orbital diffusion, a process where the solar system's orderly clockwork gradually unravels, one gravitational whisper at a time. Solar flares offer another jaw-dropping example. When the sun's magnetic field snaps, it unleashes a storm of charged particles, a tantrum that can fry satellites, knock out power grids, and blind radio communications. In 1989, a flare plunged Quebec into darkness for 9 hours, leaving millions without heat in freezing temperatures. But the real chaos lies in the chain reactions. A satellite disabled by a flare might fail to warn astronauts of radiation spikes, forcing the International Space Station to scramble for shelter. GPS signals could falter, throwing off navigation for planes and ships. Even stock markets have hiccuped during solar storms, as automated trading systems glitch from electromagnetic interference. What begins as a flicker on the sun's surface cascades into a web of disruptions, linking solar physics to subway delays and supermarket supply chains. The universe takes this sensitivity to extremes. Look at TRAPPIST-1, a star system 39 light-years away with 7 Earth-sized planets packed closer than Mercury orbits our Sun. There, the gravitational interplay is so intense that a single meteor impact on one world could destabilize the orbits of its neighbors, triggering a game of planetary musical chairs. Or ponder rogue black holes drifting unseen through galaxies. One passing near a star cluster could scatter stars like billiard balls, flinging some into the void while hurling others toward galactic centers. These aren't hypotheticals. Astronomers have traced hypervelocity stars rocketing through space at over 1 million miles per hour, their trajectories suggesting they were launched by invisible monsters lurking in the dark. Yet for all its unpredictability, this chaos isn't lawless. It follows equations we're slowly deciphering, like the three-body problem, a puzzle proving that even simple systems of 3 gravitationally linked objects move in ways no computer can perfectly predict. The cosmos thrives on these delicate instabilities, using them to shuffle planetary decks, ignite star formation, and perhaps even seed life. After all, if Earth's orbit hadn't wobbled over eons, our climate might never have cycled through ice ages, pushing evolution toward adaptable, intelligent life. The universe doesn't just tolerate chaos, it harnesses it, turning cosmic butterflies into hurricanes of creation. Deep in the wreckage of a supernova's fury, where a star has torn itself apart in one of the universe's most violent explosions, something astonishing emerges: a neutron star. Imagine taking the mass of our Sun and crushing it into a sphere no wider than Manhattan. The result is so dense that a single teaspoon of its material would weigh 1 billion tons on Earth. Yet this isn't just a lifeless hunk of matter. It spins faster than a blender's blade. Some whirl hundreds of times every second, their surfaces racing at nearly a quarter the speed of light. And as they spin, they beam radiation into space like interstellar lighthouses, pulses so regular they rival the precision of atomic clocks. What's mesmerizing is how these cosmic metronomes are born from pure chaos. When a massive star collapses, its core implodes with such force that protons and electrons fuse into neutrons, packing together until even atoms cease to exist as we know them. The outer layers rebound off this ultra-dense core in a cataclysmic supernova explosion, a fireball bright enough to outshine entire galaxies. Yet from that destruction arises near-perfect order. The newborn neutron star's rotation, inherited from the dying star's spin, gets turbocharged during collapse, like a figure skater pulling their arms in to spin faster. Magnetic fields, already intense in the original star, become trillions of times stronger during the collapse, channeling energy into narrow beams that sweep across the cosmos with every rotation. These beams are what we detect as pulsars, the rhythmic ticks of neutron stars. The Crab pulsar, for instance, flashes 30 times every second, a heartbeat left behind by a supernova observed on Earth in the year 1054. Even more extreme are millisecond pulsars, spun up to dizzying speeds by siphoning material from a companion star. Their pulses are so stable that they drift by less than 1 second over millions of years. Astronomers have used them to test Einstein's theory of relativity with precision impossible in any Earth-bound lab, watching how their signals warp as they orbit other stars or pass through the galaxy's gravitational field. But neutron stars aren't just precise, they're also laboratories for physics we can't replicate anywhere else. Under their incomprehensible gravity, matter gets squeezed into states that defy imagination. Some theories suggest their cores might contain exotic particles like hyperons or even free-floating quarks, forms of matter that haven't existed since the first microseconds after the Big Bang. Others speculate that their crusts, under immense pressure, could form nuclear pasta, structures shaped like spaghetti or lasagna sheets, the densest known material in the universe. Then there's the drama when two neutron stars collide. In 2017, astronomers witnessed such a merger for the first time, detecting not just light but ripples in spacetime itself. The event forged enough gold, platinum, and other heavy elements to outweigh Earth dozens of times over, proving that the jewelry you wear likely came from a cataclysm like this. It's a reminder that even in their death throes neutron stars create. They take the debris of stellar explosions and weave it into new possibilities: planets, life, even the very atoms that make up our bodies. So the next time you hear the steady pulse of a neutron star, remember, you're listening to the universe's most improbable symphony, a rhythm born from chaos, a beat so precise it guides spacecraft and tests the fabric of reality, all while hiding secrets about matter's most extreme forms. These stellar remnants aren't just dead stars, they're cosmic alchemists, turning destruction into order, and in their strange, spinning hearts, rewriting the rules of physics itself. Gravity is the universe's greatest choreographer, turning what looks like celestial chaos into breathtaking cosmic ballets. Consider the Milky Way and Andromeda, two spiral galaxies hurtling toward each other at 200,000 miles per hour, destined to collide in about 4 billion years. You might picture stars smashing together in a celestial demolition derby, but the reality is far more elegant. Despite containing hundreds of billions of stars each, these galaxies will pass through one another like ghosts, their stars so widely spaced that direct collisions are almost impossible. Instead, gravity will weave them into an intricate dance, stretching their spiral arms into luminous ribbons before finally merging them into a single, elliptical galaxy astronomers nicknamed Milkdromda. This isn't just a freak occurrence, it's gravity's signature move. Across the universe, galaxies cluster in groups, their motions governed by the same forces that keep planets orbiting stars. The Virgo cluster, for instance, contains over 1,000 galaxies, each tracing graceful arcs around their shared center of mass. Some, like the Whirlpool Galaxy and its companion NGC 5195, are so tightly synchronized that they've spun delicate bridges of gas and stars between them, a celestial pas-de-deux played out over millions of years. What's truly astonishing is how predictable these interactions are. When galaxies get close, gravity doesn't just yank them together randomly, it follows precise mathematical rhythms. Tidal forces stretch them into elongated shapes, while dynamical friction slows their orbits, ensuring they spiral inward rather than ricochet apart. Computer simulations show these encounters playing out with near-clockwork precision, matching what we observe in telescope images. It's as if every galaxy carries an invisible script written in the language of physics, dictating how it will move when neighbors draw near. Even more mesmerizing are the satellite galaxies that orbit larger ones like moths around a flame. The Large and Small Magellanic Clouds, our Milky Way's tiny companions, follow orbits that loop around our galaxy every 1.5 billion years. Their paths aren't random. They're sculpted by the Milky Way's gravitational field, tracing patterns as intricate as the grooves in a vinyl record. Some dwarf galaxies even orbit in planes, like planets around a star, defying expectations that they should swarm chaotically. This gravitational harmony extends beyond single galaxies. On the largest scales, galaxy clusters move in slow, stately procession along the cosmic web, their paths shaped by dark matter's invisible scaffolding. The Coma cluster, 6 times more massive than Virgo, hosts thousands of galaxies orbiting a common center, their speed so high they should fly apart, yet dark matter's grip holds them together in a gravity-bound ensemble. So when you look up at Andromeda, a faint smudge in the night sky, remember, you're witnessing a dance billions of years in the making. The universe may seem chaotic, but gravity is the silent conductor, turning collisions into choreography, chaos into cosmos. Every galactic merger, every starry swirl, is part of a grand performance, one where the music is written in the curves of spacetime itself. Imagine a planet where the sun doesn't rise and set with the steady rhythm we know instead. It wobbles unpredictably across the sky, some days blazing overhead while others vanish for years. These are the exoplanets with chaotic orbits, worlds tossed around by the gravitational tug of war between their star and neighboring planets. At first glance, they seem like cosmic disaster zones, their climates ripped apart by extreme temperature swings and violent weather. But here's the twist: some of these turbulent worlds might just be the perfect cradles for life. Take tidal heating, for example. When a planet's orbit is stretched and squeezed by gravity, the constant flexing generates heat from within, like bending a paperclip back and forth until it burns your fingers. Jupiter's moon Io, the most volcanic place in our solar system, is proof of this phenomenon. Its surface is a patchwork of erupting lava lakes, all fueled by tidal forces. Now imagine an exoplanet with a similar fate, but orbiting in the habitable zone where liquid water could exist. the internal heat might prevent its oceans from freezing over, even if its star is dim. Hydrothermal vents on Earth, thriving with life in total darkness, show how heat alone can sustain ecosystems. A chaotic orbit could turn a frigid world into a warm, geologically active oasis. Then there's climate variability. Earth's relatively stable orbit gives us predictable seasons, but what if seasons changed at random? Some exoplanets might experience millennia of tropical warmth followed by sudden ice ages, or vice versa. While that sounds catastrophic, life on Earth has survived far wilder swings. During the cryogenian period, our planet was a snowball, nearly entombed in ice, yet life persisted. Later, the Cambrian explosion saw biodiversity explode in a geological blink. Chaotic climates could drive evolution to innovate faster, favoring adaptable organisms that thrive in shifting conditions. After all, stability can breed complacency. Chaos might be the universe's way of stress-testing life. Even the wildest orbits can create pockets of stability. Picture a planet with a lopsided rotation, where one hemisphere bakes under eternal sunlight while the other languishes in darkness. The border between these extremes, the Terminator line, could host a permanent twilight zone with temperate conditions perfect for liquid water. Or consider binary star systems where a planet orbits two suns in a dizzying dance. While its path might look erratic, gravitational resonances can lock it into a stable rhythm over time, like a drummer finding the beat amid noise. The real surprise, chaos might even shield life. A planet with a shifting orbit could dodge deadly solar flares or asteroid impacts that would devastate a more predictable world. Its ever-changing position would make it a moving target in the cosmic shooting gallery. And let's not forget radiation. A turbulent magnetic field, stirred by geological chaos, could act as a protective shield against stellar radiation, far messier than Earth's neat poles, but just as effective. So while we often search for Earth-like worlds with orderly orbits, the universe might be hiding its greatest biological experiments in the places we least expect. Chaos isn't always a destroyer sometimes, it's the sculptor of strange, vibrant possibilities. The next time astronomers spot an exoplanet tumbling wildly through space, they might not be looking at a wasteland, but a laboratory where life learns to thrive against all odds. Most of the universe's patterns repeat in space spiral arms of galaxies, the orbits of planets, even the branching veins of a leaf. But what if there were structures that repeated not in space but in time? Enter time crystals, one of the strangest discoveries in modern physics. These aren't sci-fi gadgets, they're real quantum systems that oscillate between states indefinitely, like a clock that ticks forever without any energy input. Unlike ordinary crystals where atoms arrange in repeating spatial lattices, time crystals have atoms that dance to a rhythm locked into time itself. It's as if the universe stitched a hidden pulse into the fabric of reality. The magic lies in how time crystals break symmetry. Normally, the laws of physics treat all moments equally. A system shouldn't care whether it's Tuesday or Friday. But time crystals defy this. Their atoms flip between configurations at fixed intervals, creating a pattern that repeats like a heartbeat, even in the lowest energy state. Imagine pushing a child on a swing. Normally, they'd slow down and stop. A time crystal is like a swing that keeps rocking back and forth forever, not because you're pushing it, but because the universe handed it an eternal metronome. This isn't just theoretical. In 2017, scientists created the first time crystals using chains of ytterbium atoms, chilled to near absolute zero and hit with precise laser pulses. The atoms didn't respond instantly, they lagged, flipping their spins in a delayed rhythm that persisted long after the laser was gone. Later, Google's quantum computer Sycamore engineered another version, proving these exotic states could exist even in noisy, imperfect systems. The implications are staggering. If time can have structure, could the universe itself be threaded with hidden temporal patterns we've yet to detect? Time crystals might even hold clues to quantum memory. Normally, quantum information is fragile, collapsing at the slightest disturbance. But time crystals' rhythmic stability could offer a way to store data in their oscillations, like etching a message into the ticking of a clock. Some physicists speculate they could be the key to error-resistant quantum computers, where calculations unfold in sync with these crystalline time loops. Then there's the cosmic angle. If time crystals exist naturally, perhaps in the extreme conditions near neutron stars or in the vacuum of space, they could be silently marking time across the universe, their rhythms outlasting stars and galaxies. They hint at a deeper truth, that time isn't just a backdrop for events, but an active participant, with structures as rich and intricate as the spatial ones we're familiar with. So while we're used to seeing order in the arrangement of atoms or the paths of planets, time crystals remind us that the universe's patterns aren't just etched in space, they're woven into time itself. And as we uncover more of these temporal architectures, we might find that chaos was never the opposite of order, just order playing out in dimensions we're only beginning to perceive. The concept of the multiverse stretches our understanding of reality to its limits. What if our universe is just one page in an infinite cosmic library, each volume written with different physical laws? Some versions might have gravity 1 billion times stronger, rendering planets impossible. Others could be nothing but a sea of dark matter, devoid of stars or light. At first glance, this seems like the ultimate chaos, a cosmic dice roll with no rules. But dig deeper, and you might find a hidden architecture threading through the madness, a structure so vast it makes our universe look like a single brushstroke in a galaxy-sized painting. Take string theory's vision of the multiverse, where each possible universe arises from the way extra dimensions curl and fold. These aren't random twists, they're solutions to precise equations, like different notes played on a vibrating string. Even in this sea of possibilities, only certain configurations are stable enough to sustain universes long enough for stars and life to emerge. It's as if the multiverse has a built-in filter, favoring order amid the noise. Or consider the bubble universe model, where new universes bud off from old ones in an endless cycle. Each may have unique constants, but the process itself, inflationary expansion, follows predictable mathematical rules. Chaos here isn't lawless, it's generative, a factory assembling realities along an assembly line of physics. Then there's the quantum multiverse, where every decision forks reality into new branches. Sounds messy, right? Yet even here, patterns emerge. The many worlds interpretation suggests these branches aren't random, but unfold via the strict probabilities of quantum mechanics. A universe where you turned left instead of right isn't a free-for-all. It's a divergence weighted by equations as precise as the ones guiding electrons. Some physicists even speculate that these branching paths might eventually loop back, weaving a tapestry where all possibilities interconnect in higher dimensions. But the most tantalizing clue to hidden order comes from the anthropic principle. Of all possible universes, why does ours seem so finely tuned for life? One answer, perhaps only the universes with the right conditions produce observers to ask the question. In this view, the multiverse isn't a chaotic jumble but a grand sorting mechanism, with life acting as a sieve that selects for stability. It's not that the laws of physics are random, it's that we're standing in the tiny fraction where they line up just right. What's breathtaking is that we might already have evidence of other universes. The cold spot in the cosmic microwave background, An unusually frigid patch of sky could be a bruise from a collision with a neighboring universe. Certain gravitational wave signals might carry echoes of pre-Big Bang events in a parent cosmos. Even the mysterious dark flow, where hundreds of galaxy clusters stream in the same direction, hints at gravitational tugs from beyond our cosmic horizon. These aren't just anomalies, they're potential fingerprints of a multiverse operating by rules we're only beginning to glimpse. So is the multiverse the last word in cosmic chaos, or a higher dimensional order we can't yet see? The answer might lie in between a spectrum where randomness and structure intertwine. After all, a snowflake looks chaotic up close, but zoom out, and you'll see the symmetry of its design. The multiverse could be the same, a storm of possibilities, yes, but one where every raindrop falls according to a deeper, more beautiful logic. And if that's true, then even in infinity, the universe hasn't run out of patterns, just waiting for us to find them. The cosmic web is the universe's grand blueprint, an immense, delicate lattice where galaxies cling like fireflies to invisible threads. Stretching hundreds of millions of light years, these filaments of dark matter weave through the void, connecting galaxy clusters in a network so vast it makes the internet look like a child's scribble. But this isn't just a pretty arrangement. It's the universe's way of turning primordial chaos into cosmic order, a gravitational highway system that's been shaping the cosmos since the first stars flickered to life. Picture the aftermath of the Big Bang, when the universe was a seething, nearly uniform soup of particles, tiny quantum fluctuations, imprints left over from inflation created slight overdensities, regions where matter was ever so slightly more crowded. Over billions of years, gravity amplified these wrinkles, pulling matter into dense knots along intersecting lines. The result: a three-dimensional web where filaments intersect at galaxy clusters, the bustling metropolises of the cosmos. The Virgo cluster, for instance, sits at a junction where multiple threads converge, home to over 1,000 galaxies bound together by dark matter's unseen hand. What's astonishing is how efficiently this web channels matter. Gas flows along filaments like water through pipes, funneling fuel into galaxies and igniting star formation. Some astronomers compare it to a circulatory system, with dark matter as the bones and ordinary matter as the blood. The Spiderweb galaxy, a massive protocluster 7 billion light-years away, shows this in action. Dozens of smaller galaxies line up along a dark matter filament, streaming toward a central hub like commuters drawn to a downtown core. But the web isn't static. It vibrates with motion, galaxies sliding along filaments in a slow-motion ballet. The Great Attractor, a mysterious gravitational anomaly, is pulling the Milky Way and thousands of other galaxies toward it at over 1 million miles per hour. We can't see what's tugging us, but the cosmic web structure suggests it's a supercluster hidden behind the dust of our own galaxy. A reminder that even the grandest motions are written into this invisible lattice. Perhaps the most mind-bending twist is how the cosmic web mirrors other networks in nature. Neurons in the human brain branch in eerily similar patterns, as do the root systems of fungi and even synthetic models of the internet. It's as if the universe has a favorite way to build complexity, whether it's organizing galaxies or transmitting signals between cells. This isn't just coincidence. It's a clue that the same mathematical rules govern growth at every scale, from the quantum to the cosmic. Zoom out far enough, and the cosmic web reveals its ultimate purpose. It's the universe's way of fighting entropy. By concentrating matter into structured pathways, it ensures stars have the fuel to burn, galaxies the gravity to spin, and life the ingredients to emerge. Chaos might reign in the voids between filaments, but the web itself is a masterpiece of order, a silent, sprawling architecture that's been under construction since the dawn of time. And every galaxy, every star, every atom in your body owes its existence to this hidden framework, the universe's answer to the chaos of creation. Quantum entanglement is like the universe's ultimate magic trick, two particles separated by vast distances, somehow dancing in perfect sync without any visible connection. Einstein famously dismissed it as spooky action at a distance, but today we know this phenomenon isn't just real, it's one of the cosmos's most fundamental patterns. Imagine tossing a pair of gloves into opposite ends of the galaxy. Open one to find a left hand, and instantly, without any signal or delay, the other becomes a right. That's entanglement, a hidden thread stitching the fabric of reality together, defying our everyday intuition about how space and time should work. What makes this even wilder is how entanglement plays out in the quantum realm. Take two electrons spun together so their properties are linked. Separate them by light years, measure one's spin, and the other will instantly mirror it, not because some signal traveled faster than light, but because their states were never truly independent to begin with. It's as if the universe cheated, pre-writing their fates as a single equation. This isn't just theoretical. Experiments with photons, atoms, and even tiny diamonds have proven entanglement again and again, with particles coordinating across labs, cities, and even satellites in orbit. But here's where it gets cosmic. Entanglement isn't just a lab curiosity, it might be the glue holding spacetime itself together. Some theories suggest that the fabric of the universe, from the smallest scales to the vastness of black holes, is woven from entangled quantum bits. Picture spacetime as a tapestry, with each thread a connection between particles. When entanglement spreads, it could literally stitch new space into existence, like a cosmic loom weaving reality moment by moment. Black holes push this idea to the extreme. When matter falls in, its information isn't lost, it's scrambled into a quantum fog on the event horizon, entangled with radiation leaking back out. This holographic principle hints that the three-dimensional universe we see might just be a projection of entangled data written on a two-dimensional surface. And entanglement isn't picky about distance. Particles entangled at the birth of the universe could still be linked today, their faces intertwined across billions of light years. This raises a jaw-dropping possibility. What if entanglement is why the cosmos looks so uniform? The cosmic microwave background, that snapshot of the infant universe, shows nearly identical temperatures everywhere, too uniform for distant regions to have ever been in contact. Unless, of course, they were quantum-connected long before space expanded. Yet for all its mystery, entanglement is already shaping our future. Quantum computers harness it to perform calculations no ordinary machine could, solving problems like drug discovery or climate modeling in seconds. Cryptographers use it to create unhackable codes where any eavesdropper would instantly break the entanglement, leaving a telltale sign. Even our understanding of gravity might rely on it. Some physicists think gravity itself emerges from the universe's vast web of quantum links. So the next time you feel alone under the night sky, remember, the universe is far more connected than it appears. Particles separated by galaxies might still whisper to each other, bound by threads we're only beginning to trace. Einstein called it spooky, but entanglement isn't a ghost story. It's the universe's way of reminding us that separation is an illusion, and deep down, everything is part of the same shimmering whole. A supernova is nature's ultimate paradox, a cataclysmic explosion so violent it outshines entire galaxies. Yet without these eruptions of chaos, the cosmos would be a sterile wasteland. When a massive star reaches the end of its life, it doesn't fade quietly. Instead, it detonates with the force of a billion suns, hurling its guts across space at nearly a tenth the speed of light. In that single, searing moment, the star forges elements heavier than iron gold for your jewelry, uranium for reactors, even the calcium in your bones. These atoms, born in the heart of stellar Armageddon, become the raw materials for new worlds. It's as if the universe took destruction and turned it into a factory for creation. Consider the Crab Nebula, the glittering aftermath of a supernova witnessed on Earth in the year 1054. Today, its expanding cloud of gas and dust stretches nearly 10 light-years across, threaded with filaments of oxygen, carbon, and neon. But this isn't just debris, it's a stellar nursery. Shock waves from the explosion compress nearby gas clouds, triggering the collapse of new protostars. The same blast that obliterated a star is now sculpting its replacements like a phoenix, ensuring its own rebirth. Supernovas don't just build, they regulate. Their explosions heat the interstellar medium, preventing gas from cooling too quickly and collapsing into stars all at once. Without this feedback, galaxies would burn through their fuel in frenzied bursts, leaving no time for planets or life to form. The Milky Way's delicate balance of star formation owes its existence to these periodic detonations, each one a cosmic pressure valve ensuring the galaxy doesn't overheat or stagnate. There's an even grander scale at work. When multiple supernovas erupt in concert, their combined force can carve vast bubbles in the galaxy, like the local bubbles surrounding our solar system. This cavity, spanning 1,000 light-years, was likely blown clear by a chain of explosions millions of years ago. Inside this pocket of sparse gas, stars, including our Sun, drift in relative safety, shielded from the denser, more turbulent regions where supernovas are frequent. We quite literally owe our stable cosmic neighborhood to the chaos that came before. But the most astonishing twist lies in the supernova's role as a cosmic alchemist. Before these explosions, the universe was mostly hydrogen and helium, the simple ingredients cooked up in the Big Bang. Supernovas changed everything. They peppered the cosmos with heavy elements, enriching each generation of stars with more complexity. The iron in your blood, the silicon in Earth's crust, even the iodine in your thyroid, all were forged in the hearts of dying stars and scattered by their violent ends. So when you look up at the night sky, remember, every glittering star, every swirling nebula, even the atoms in your body, are the legacy of chaos harnessed into order. Supernovas aren't just destroyers, they're the universe's way of recycling itself, turning death into the building blocks of life. The cosmos doesn't just tolerate these explosions, it depends on them, weaving their fury into the very fabric of existence. Dark energy is the universe's greatest vanishing act, a mysterious force that makes up nearly 70% of everything in existence, yet we can't see it, touch it, or even explain what it truly is. Imagine blowing up a balloon with invisible ink, watching it expand faster and faster, but having no idea what's filling it. That's the puzzle astronomers face. In the late 1990s, two teams studying distant supernovas made a jaw-dropping discovery. The universe isn't just expanding, it's accelerating, as if some unseen hand is pressing harder on the cosmic gas pedal with each passing moment. That hand is dark energy, and its fingerprints are everywhere, from the stretching fabric of space to the way galaxies drift apart like ships on an invisible tide. At first glance, dark energy seems like the ultimate wild card, a featureless, uniform push that treats every corner of the cosmos the same. But what if there's more to it? Some theories suggest dark energy isn't just a static force but could fluctuate over time or space, leaving subtle patterns in its wake. Think of it like wind. Sometimes it's a steady breeze, other times it gusts unpredictably. If dark energy has similar variations, they'd be etched into the large-scale structure of the universe. subtly warping how galaxies cluster or how light bends across cosmic distances. The Euclid Space Telescope, launched in 2023, hunts for these very distortions, mapping billions of galaxies to see if dark energies grip tightens or loosens across different epochs. Then there's the eerie coincidence of the cosmological constant, the idea that dark energy's density stays the same even as the universe expands. Einstein originally proposed this concept to keep the universe static, then abandoned it when Hubble proved expansion was real. Now it's back in vogue as the simplest explanation for dark energy, but the math reveals something unsettling. The observed value of this constant is absurdly tiny compared to what quantum theory predicts. It's like measuring the weight of a mountain and getting the answer as light as a feather. This mismatch hints that dark energy might not be constant at all, but a dynamic field evolving under rules we've yet to uncover. One provocative possibility is that dark energy is tied to the quantum foam, that bubbling sea of virtual particles popping in and out of existence. If this foam's energy contributes to dark energy, it could mean the vacuum of space isn't empty but simmering with activity, driving expansion from within. Alternatively, dark energy might be a new fundamental force, a sibling to gravity and electromagnetism that only reveals itself on cosmic scales. Some models even suggest it's the precursor to a big rip, where expansion eventually tears apart galaxies, stars, and even atoms. The most tantalizing clue lies in the cosmic microwave background. Tiny temperature fluctuations in this ancient light hold imprints of dark energy's early influence. By comparing these patterns with the distribution of galaxies today, scientists can trace how dark energy's push has changed over billions of years. Already, there are whispers in the data, anomalies where the universe's expansion doesn't quite match predictions. Could these be hints that dark energy isn't as uniform as we thought, or evidence of something even stranger, like a fifth dimension leaking into our own? What's certain is that dark energy isn't just an academic curiosity. It's the architect of the universe's fate, deciding whether our cosmos will fade into cold emptiness or unravel in a catastrophic crescendo. And as we peel back its secrets, we're not just solving a puzzle, we're reading the hidden rhythms of reality itself, written in the stretching spaces between the stars. Magnetism is the universe's silent conductor, orchestrating chaos into harmony with invisible threads of force. Picture a nebula, a swirling cloud of gas and dust where stars are born. At first glance, it seems like a turbulent free-for-all, but hidden within that chaos are magnetic fields, stretching across light years like cosmic guitar strings. These fields channel the gas into orderly streams, guiding collapsing material into dense knots that ignite as newborn stars. Without magnetism, these stellar nurseries would be shapeless blobs, their gas too scattered to ever coalesce into something as precise as a solar system. Take the iconic pillars of creation in the Eagle Nebula. Towering columns of gas stretch 4 light-years high, their surfaces sculpted by the interplay of gravity and magnetic pressure. Like invisible scaffolding, magnetic fields hold these structures upright, resisting the destructive force of nearby stellar winds. The result, a celestial incubator where stars form in neat, nested pockets, their births timed and placed by magnetism's unseen hand. Even the jets of plasma erupting from young stars, those dazzling, light-year-long fountains, are collimated by magnetic fields, focused into narrow beams as straight as laser pointers. Galaxies, too, dance to magnetism's tune. The Milky Way's spiral arms aren't just shaped by gravity, they're threaded with magnetic fields that align interstellar dust like iron filings around a magnet. These fields act as cosmic highways, steering cosmic rays and regulating star formation. In the galaxy's heart, near the supermassive black hole, magnetism becomes even more dramatic. There, fields twist into colossal loops, channeling superheated plasma into jets that punch clear through galactic space, visible across the universe. But perhaps magnetism's most astonishing feat is how it tames turbulence. In the Orion Nebula, supersonic winds roar through gas clouds at hundreds of miles per second, enough to tear any structure apart. Yet, thanks to magnetic fields, this chaos is harnessed. The fields act like shock absorbers, dissipating energy in precise waves that prevent total fragmentation. It's why star-forming regions don't just explode into disarray, but instead condense into elegant disks, the birthplaces of planets. Even dying stars bow to magnetism's rule. When a massive star collapses into a neutron star, its magnetic field doesn't vanish, it's amplified 1 trillion times, turning the star into a pulsar. These spinning powerhouses beam radiation along their magnetic poles, flashing like lighthouses with a regularity that rivals atomic clocks. Some magnetars, neutron stars with even stronger fields, generate flares so intense they can strip atmospheres off planets light years away. Yet, for all their ferocity, these outbursts follow magnetic field lines, their violence sculpted into predictable arcs. From the smallest plasma eddies to the largest galactic jets, magnetism is the universe's way of writing straight with crooked lines. It takes the raw chaos of cosmic forces and bends them into patterns that build stars, shape galaxies, and perhaps even pave the way for life. So the next time you gaze at the night sky, remember, what looks like random starlight is really a masterpiece, painted stroke by the quietest artist of all. Gravitational waves are the universe's way of whispering its secrets, ripples in the very fabric of space-time, born from the most cataclysmic events imaginable. Picture 2 black holes, each heavier than stars, locked in a death spiral. As they circle each other hundreds of times per second, their immense gravity warps space-time like a spinning paddle churning water. When they finally collide, the impact unleashes energy equivalent to converting 3 suns into pure space-time vibrations in a fraction of a second. These waves race outward at light speed, stretching and compressing everything in their path, including Earth, where detectors like LIGO and Virgo catch these faint tremors from billions of light years away. What's astonishing isn't just the violence of these events, but their precision. Einstein predicted gravitational waves a century ago, yet even he doubted we'd ever detect them. The math said these ripples would distort spacetime by less than 1,000th the width of a proton, a change so small it's like measuring the distance to Alpha Centauri with an error no wider than a human hair. But in 2015, LIGO proved Einstein right, capturing waves from a black hole merger 1.3 billion light-years away. The kicker, the signal matched his equations to near perfection, right down to the chirp, the rising pitch as the black holes spiraled inward. Chaos, it turns out, follows a script. These waves aren't just cosmic echoes, they're telescopes for the invisible. When 2 neutron stars collided in 2017, gravitational waves arrived at Earth 2 seconds before a gamma-ray burst, confirming light and spacetime ripples travel at the same speed. The aftermath glowed with heavy elements like gold and platinum, proving these collisions are cosmic forges. But the real surprise came when astronomers pointed traditional telescopes at the spot. No black hole formed. Instead, the merger left a hypermassive neutron star, a fleeting object that shouldn't exist under old models. Gravitational waves didn't just confirm theories, they exposed gaps in them, pushing physics forward. Even stranger are the waves we can't yet explain. Some detections show black holes merging at angles or speeds that defy expectations, hinting at unseen populations lurking in the dark. Others, like the potential boson star collision of 2020, ripple with frequencies that don't match any known object. Then there's the background hum, a collective buzz from countless distant mergers, like hearing a stadium crowd from miles away. This noise could reveal how often black holes paired up in the early universe, or even expose primordial black holes from the Big Bang itself. But the grandest revelation: gravitational waves paint space-time as a dynamic medium, one that vibrates and resonates like a drum. When black holes merge, they don't just vanish. They ring, sending out harmonics that reveal their mass, spin, and even shape. It's as if every cosmic catastrophe leaves a fingerprint, one we're only now learning to read. And with new detectors like LISA, a space-based observatory, we'll soon tune into lower frequencies, catching the mergers of supermassive black holes and perhaps even waves from the universe's birth. So while black hole collisions might seem like ultimate chaos, their gravitational waves tell a different story, one of structure, predictability, and a universe that, no matter how violent, never stops speaking in equations. Every ripple is a reminder. Even the darkest corners of the cosmos play by rules we can understand, if only we learn to listen. Life thrives in places where it shouldn't, deep in boiling acid, under crushing ocean pressures, even inside the radioactive wreckage of nuclear reactors. These extremophiles, Earth's ultimate survivors, hint at something astonishing. Life isn't a fragile accident, but a stubborn pattern the universe keeps repeating. Take tardigrades, microscopic water bears that can endure the vacuum of space, or Deinococcus radiodurans, a bacterium that laughs off radiation doses 1,000 times lethal to humans. If life can flourish in Earth's harshest corners, why not in the sulfuric acid clouds of Venus or the subsurface oceans of Europa? The cosmos might be teeming with organisms we've yet to recognize, not despite the chaos, but because of it. Consider the raw ingredients. Complex organic molecules, the building blocks of life, are everywhere. They've been found in meteorites swirling around newborn stars, even in the frigid voids between galaxies. Amino acids like glycine hitch rides on comets, while the Rosetta mission discovered phosphorus, a key element for DNA, on Comet 67P. These aren't rare exceptions, they're cosmic norms. The universe seems obsessed with assembling life's puzzle pieces, scattering them like seeds across space and time. Then there's panspermia, the idea that life hitchhikes between worlds. When a meteorite from Mars landed in Antarctica, scientists found structures resembling fossilized bacteria inside, controversial but tantalizing. If microbes can survive interstellar journeys shielded inside rocks, then life might not start from scratch on each planet. Instead, it could spread like cosmic wildfire, jumping from one habitable oasis to another. The implications are staggering. Earth's biosphere might not be unique, but one branch of a galactic family tree older than the solar system itself. Even the chemistry of life suggests deeper order. All known organisms use the same 20 amino acids, the same DNA structure, even the same chirality, their molecules left-handed like a cosmic signature. Is this mere coincidence or evidence of a universal template? Some theories suggest life's building blocks form most readily under certain cosmic conditions, like how snowflakes always grow 6 arms, no matter where they fall. If true, alien life might not be randomly different, but eerily familiar. Its biology channeled by the same fundamental rules that shape spiral galaxies and quantum foam. The ultimate clue lies in life's timing. Earth formed in a bombardment of asteroids and lava, yet fossils show microbes appeared almost the instant the planet cooled. Statistically, that's suspiciously fast, like the universe was waiting for the chance. Combine that with the sheer number of potentially habitable worlds, billions in our galaxy alone, and the odds tilt heavily toward life being not just possible but inevitable. Chaos doesn't suppress biology, it incubates it, testing countless variations until something sticks. So when we search for extraterrestrial life, we're not just hunting for aliens. We're testing whether biology is woven into the universe's fabric, a pattern as fundamental as gravity or light. From boiling vents to frozen moons, life keeps proving it's not a fluke, but a force. One the cosmos has been cultivating since the first stars lit up the dark. Simulating the universe is like trying to reconstruct a symphony from a single note. We have the basic laws of physics, but the sheer complexity of cosmic evolution defies simple prediction. Supercomputers like Frontier and Fugaku now run simulations with trillions of particles, recreating how galaxies form, black holes merge, and dark matter weaves its invisible web. These digital universes aren't just academic exercises, they're stress tests for our understanding of reality, probing whether chaos can ever be fully tamed by equations. Take the Illustris TNG project, one of the most ambitious cosmic simulations ever attempted. It starts with a virtual soup of particles resembling the early universe, then lets gravity, hydrodynamics, and magnetism run their course over billions of simulated years. The result, spiral galaxies emerge with uncanny accuracy, their arms curling into familiar Fibonacci spirals. Black holes grow at their centers, regulating star formation just as they do in the real cosmos. Even the cosmic web, the vast filamentary structure of the universe, materializes in the simulation's void, matching telescope observations down to the finest details. It's as if the universe's chaos isn't random at all, but a puzzle with pieces that snap together in predictable ways. Yet for all their precision, these simulations hit walls. The small-scale crisis in cosmology reveals a glaring mismatch. Simulated galaxies end up with fewer satellite galaxies than we observe in reality. Some argue this points to flaws in our models of dark matter, while others suggest overlooked physics like primordial magnetic fields or exotic particle interactions. Then there's turbulence, the chaotic swirl of gas in star-forming regions which even the fastest supercomputers struggle to render at full fidelity. Simulating a single molecular cloud in true detail could take longer than the age of the universe, forcing scientists to approximate. It's a humbling reminder that the cosmos operates at resolutions we can only dream of replicating. The real frontier lies in quantum gravity simulations, where researchers like those at the Perimeter Institute model spacetime as a network of tiny, interconnected loops. These simulations suggest that at Planck scales, spacetime might foam and fluctuate like an ocean in a storm, with wormholes blinking in and out of existence. If verified, this could explain how black holes reconcile Einstein's smooth spacetime with quantum mechanics graininess. But here's the catch. Even these cutting-edge models rely on simplifications, trading absolute accuracy for glimpses into realms beyond experimental reach. What's fascinating is how simulations also uncover emergent order. In the Eagle project, virtual galaxies self-organize into structures that obey observed scaling laws, like how a galaxy's mass relates to its rotation speed, without programmers explicitly coding those rules. This hints that certain cosmic patterns aren't just imposed by initial conditions, but arise naturally from underlying physics, like flocking birds creating intricate formations from simple individual behaviors. Chaos, it seems, has a knack for weaving its own tapestry of order when left to evolve. So can we ever fully model the universe, perhaps not in every atom's detail? But each simulation, each approximation, brings us closer to decoding the hidden algorithms the cosmos runs on. The goal isn't to eliminate chaos, it's to understand its grammar, the way a poet learns to harness the wildness of language into verse. And with every iteration, we're not just predicting the universe, we're learning to speak its language. From the quantum foam bubbling beneath spacetime to the vast cosmic web knitting galaxies together, we've traced the universe's hidden blueprints, the delicate equations that transform chaos into creation. Think of a supernova's fury forging the iron in your blood, or the gravitational dance of black holes ringing spacetime like a bell. These aren't exceptions to the rules, they're proof that the cosmos thrives on balance, where turbulence and symmetry exist in a perpetual waltz. Even entropy, the so-called arrow of disorder, carves pathways for new complexity, from swirling galaxies to the neurons firing in your brain. Consider how far we've come. Once, lightning was the wrath of gods and eclipses omens of doom. Now we decode the fractal patterns of nebulae and listen for gravitational waves from colliding stars. Yet every answer unveils deeper mysteries. Dark energy accelerates the universe's expansion, but why? Quantum entanglement links particles across light years. How? The more we learn, the clearer it becomes. Chaos is just order we haven't deciphered yet. So the next time you look up, remember, you're not just stargazing. You're witnessing a grand performance where every supernova, every spinning pulsar, every invisible thread of dark matter plays its part. The universe doesn't hide its secrets out of spite. It invites us to look closer, to listen for the rhythm beneath the noise. And as we keep exploring, who knows what harmonies we'll uncover next? If this journey through the cosmos's hidden order resonated with you, let us know in the comments what celestial puzzle leaves you awestruck. Don't forget to like, subscribe, and join us as we keep unraveling the universe's greatest enigmas, one discovery at a time. The cosmos is speaking. Are you listening?